Okay, airframe in good condition.
Yep.
The bays closed.
Yep.
Motor screws tight.
Yep.
Prop bolt tight.
Yep.
Other hardware accounted for.
Yep.
Control rod straight. Cameras have SD cards.
Yep.
Okay, DCS displays correct aircraft. What have you done to this now then? Do I need to just execute again, yeah?
Yep. AggieAir is the autonomous remote sensing system. It takes off completely autonomously, flies around according to a pre-programmed flight plan, takes pictures while it's flying, and then also lands completely autonomously. And then afterwards you can take the pictures and generate a geo-rectified mosaic with them.
The idea for AggieAir was conceived at the Utah Water Research Laboratory at Utah State University. The lab addresses water-related issues through research and fieldwork. Mac McKee, the lab's director, was looking for a solution to a remote sensing problem.
Approximately 4 years ago, we had need of remote sensing capabilities that would allow us to acquire an estimate of soil moisture over large irrigated areas.
He saw a need for, giving farmers some sort of platform, a remote sensing platform that they could use to give them feedback about soil moisture so that they can water more efficiently.
And we decided that we would build our own fleet of UAVs. The aircraft had to be inexpensive, they had to be easy to use, and processing of the imagery acquired from the aircraft had to be relatively simple. And that's what set us upon this quest for AggieAir.
They looked internally to the university and found Dr. Yang Chuan Chen.
Dr. McKee shared with me his philosophy regarding water management. He said, if you cannot measure, you cannot manage. So the question is how to measure. So naturally, I proposed to use unmanned air vehicles, so that those unmanned air vehicles serving as flying sensors to check those conditions.
Dr. Chen then started a project that was funded by MAC to develop a remote sensing platform. That's where I came in. I was one of Dr. Chen's students, and one of the first ones on the project. Me and a group of students then developed the platform at CSIS within a couple of years.
The platform is designed to fly following a pre-programmed flight plan autonomously. While the drone is in the sky, it takes pictures of the landscape below every 4 seconds. Upon completion, the drone will return back to the ground station with the images it captured.
Now, 4 years later, we have applications and paid contracts in a number of different water management areas, and irrigated agriculture is one of them.
Soon after the development of the AggieAir platform, the team found that many other sectors of research could use a platform for a variety of applications. We will discuss 5 main applications that have benefited from the AggieAir technology. The first one we will discuss is civil applications, which consists of surveying, monitoring, and documenting construction and the condition of existing infrastructure.
One of the problems that most entities of hydraulic structures have is that they don't often have real current imagery of their structure, of their pipeline, of their dam. The imagery might be older, it might be out of date, And so almost everyone is interested in up-to-date imagery that has high resolution and of high quality, that you can look for things that you may not have noticed from the ground.
Steve Barfus, a professor at USU, is working on a project with the Utah Department of Transportation to investigate how AggieAir can assist the department in wetland mitigation, inventory control, and documenting construction.
One of the things we've done is we've performed a structure inventory for them, in which we've used AggieAir to take high resolution imagery of things like culverts, guardrails, signs, striping on the roads, and they use that information to assess things that are good and bad about their highway structures.
In southern Utah, AggieAir flew multiple times and mapped a new highway before, during, and after construction. Multiple flights provided the Utah Department of Transportation with a series of mosaics that document the progression of the construction and the final as-built highway.
It allowed them to see the staging areas of their construction, to gain a historical record of the construction process. It also allowed them to evaluate alignments and look at quality, and it was almost near real time. We were able to give them the imagery just a few days after the flight was taken.
It's in standby now, yeah. Throttle 76.
Is it red though? That means the kill throttle's on if it's red.
Green and red. The resurrect.
Yeah, that's the one.
Okay, I pressed it. Okay, we're good.
So now it's not red anymore, right?
No.
Okay. Everything's good now. But, so every time a picture's taken, image number 2, you've got ground speed, heading, latitude, longitude, altitude, position accuracy of the GPS, vertical speed, phi, theta, psi, which is the angles that it's, so roll, pitch, and yaw.
Each time an image is captured, the position and orientation data from the onboard navigation sensors are recorded and used to automatically roughly georeference each image after the flight. This data is also used to stitch and generate a highly accurate orthorectified mosaic.
After about an hour's worth of flight, we may have 350 to 400 images. The best solution and the most accurate is to take all of the images together, stitch them together into one large image. And then not only do you have that large image, but it's georeferenced. So that means that it actually lies on the earth where it's supposed to go. And not only that, I could measure one side of the building to the other, and I would know exactly how wide the building is.
When the UAV finishes its flight, the images, coupled with their position and orientation data, are taken from the cameras and given to Shannon Clemens, a photogrammetrist and GIS specialist, for post-processing.
Once I get the photos in my possession, we put them into a software, and here we look at each individual frame. These images are placed on the earth roughly georectified. They probably have a 10-meter error.
This is georectified only with the position orientation of the plane. And see, they sort of line up pretty well, right? The reason that they don't line up perfectly is because we don't know perfectly where we're at. You know, we don't have a perfect estimation of our position. The GPS sensor has error, and also the IMU has error as well. So that error is projected onto the ground, and that's where we get these errors.
The images are taken from that point and processed with some additional software called ENSO Mosaic.
So once I do the levels and iterations in ENSO Mosaic, and I put in the ground control points to help orthorectify it, we can have a final product,
which they can overlay into Google Earth or put into their GIS.
For many of their projects, Shannon has been able to finish an ortho-rectified mosaic of a 5-mile river or a 3 square mile area with only 6 hours of processing. AggieAir's capability to map quicker at a high resolution and a lower cost is desirable to hydraulic modelers and other river surveyors and researchers who have found it very useful in vegetation mapping, substrate classification, hydraulic modeling, river restoration, and fish habitat mapping. Joe Wheaton, an assistant professor in watershed sciences and researcher in fluvial geomorphology, has used the AggieAir platform for various projects. On one occasion, he and a team used it to evaluate an experiment they were doing in the John Day Basin in Oregon.
So we've got a little problem on Bridge Creek in that the system is incised, and so it's cut down into its alluvial valley in this floodplain. And when you have incision like that, what happens is it disconnects the channel from its former floodplain. And so where you might have had a big riparian corridor before with lots of diversity of tree species and providing habitat for lots of different upland terrestrial organisms, as well as providing good cover and shade for fish, when you incise this system down, you disconnect that, you lower the water table, and then you end up with a much more homogenized habitat, and in this case it's sort of a ditch. And so it happens not to be very good for steelhead in this case.
Dr. Michael Pollock had the idea that if they could employ the local beaver population to build beaver dams, then maybe the dams would fill up with sediment and could reconnect the flow from an incised river back to its floodplain to benefit the steelhead population. The team went out and embedded wooden posts in the river in hopes that the beavers would use these poles as anchors for dams that would eventually transform the river and improve habitat. In just a year, the preliminary monitoring results, aided by AggieAir, suggest that the experiment has been successful so far.
We did a full-blown implementation project, and one of the things that Austin's helping us with is we're monitoring that in a lot of different ways. So we're going out and we're collecting topography and looking at how that thing degrades through time. But a picture is worth 1,000 words, and if we can have repeat imagery and see those changes as a result of all these structures and beaver dams going in, then it helps us quantify and tell that story in a much more compelling way. So that's the regular Google Earth imagery there. We turn on Austin's imagery, so it's just much better resolved. And what you can actually see in his imagery here, these little structures are beaver dams and beaver dam structures.
As evident in the Beaver Project, the riparian area is constantly changing depending on flow, which is why up-to-date imagery can be so important to people managing riparian areas.
So this is some example of imagery that we were acquiring with a blimp, but this was really labor-intensive for us. It would take us, at least a half a day per kilometer to go out and set targets and get all this imagery, and then a lot of post-processing, because we're using a little blimp with a regular camera attached to it, and we're just taking tons of pictures. Where Austin's stuff comes in and where AggieAir comes in is that they've got this, that drone, where it would take us like a half a day, at least up to a day to do a whole reach, they could survey 25 kilometers in a morning for us.
Another benefit of the AggieAir platform is that it can provide a near-infrared mosaic of the surveyed area.
If you have visual and near-infrared imagery together, you can use it to help you classify different types of hydrology. The water itself absorbs a lot of the near-infrared light, where the vegetation reflects a lot of it. So you can clearly see a little tiny channel here where from the visual it's not so clear.
Although the near-infrared imagery has proven useful in many applications, it was originally included in the platform to quantify soil moisture over large irrigated areas so that better information about near-term irrigation water demands would be available to canal and reservoir operators. The imagery supplied by AggieAir can be given to a set of fairly sophisticated algorithms that uses the color and the near-infrared imagery to generate estimations of root zone soil moisture over large areas and to forecast how soil moisture will change over time.
Our target, though, is the operation of long canals and reservoirs that are all upstream of the farmland.
The local canal and reservoir operators have trouble anticipating farmers' demands, so that water can be released from reservoirs and diverted into canals to reach the farmer at the times and in the quantities needed while minimizing water losses from the canal system.
Anticipating short-term demand for irrigation water is a complicated issue.
We expect that using the RGB near-infrared, we're going to be able to pull out soil moisture data from that.
The soil moisture data could also help farmers to better estimate when and how much water to order so that it arrives the day they need it and in more appropriate quantities. Wetlands are natural occurring saturated areas with very diverse ecosystems. One significant problem wetland managers have is managing non-native invasive plant species, such as Phragmites.
It's a reed or large grass species that is invasive and is causing serious problems in wetlands all across North America and many other places in the world. It outcompetes species that have tremendous value as habitat for migratory waterfowl and other kinds of valuable wetlands animals. This is a problem for a wetlands manager, just knowing where all that stuff is.
What we can do is not only give them the visual imagery, but we can give them the near-infrared imagery, but you can also then take it a step further and actually use the two images to automatically classify the plant species that you're interested in. The red indicates where the non-native Phragmites is.
We flew this particular site 4 times a year within a growing season, and we're going to detect changes where the Phragmites is, where it's growing.
And we can see the effects of their control attempts and help them begin to evaluate what they can do and what they can do better and where might be optimal to apply different kinds of control measures.
Another wetlands application involves construction. If a construction project will remove a wetland area, the legal protocol insists that the area be surveyed to determine and quantify what species will be destroyed. The wetland destroyed must then be replaced at a different location to help balance the effects on the environment.
We are planning this summer to take high-resolution imagery of a proposed highway corridor, and that corridor is proposed to go through a wetlands area. And with wetlands mitigation, whenever you destroy a wetland, you have to replace it somewhere else.
They have difficulty in understanding and measuring what kinds of wetland plants are displaced or would be displaced by a road, and in actually quantifying that.
The high-resolution imagery and the classification process that we use is near 95% accurate, and that accuracy allows the DOTs to save a lot of money.
They think that we might be able to reduce the cost of their wetland set-aside program by 50% or more.
I'm not saying a word.
Alright, fine. So, you can see it flying around, you can see where the plane currently is, and you can see where it wants to go. But then all of the waypoints in the flight plan and the maps are downloaded off Google Earth, so that you can kind of see about where it is that way. And you can zoom out and see all the little waypoints and stuff. But in addition to looking at where the plane's flying around, you can see the voltage of it here. There's the speed. It's currently going 18 meters per second, which is like 35 miles an hour. The throttle percentage, 66%, above ground altitude, and a bunch of other things. So here's the ground station. This is what we use to monitor what's going on with the plane, but we also use this to send commands to the plane. For example, if the customer said, I want to cover this river from this point to this point down here, the first thing I would do is measure the width of the river. So it's about 600 meters wide. There's two different things you can do. You can fly high enough to cover the whole 600 meter wide swath, or you can do it in 2 flight lines. In this case, I would choose to cover this whole river in 1 flight line. I mean, it's a pretty wide river, and so we'd have to probably fly it at 1,000 meters. What I'll do is draw a polygon around this, what I have to do is make sure that this polygon is about 600 meters wide. So I'll measure at each corner point just to see where 600 meters is. I'll actually adjust the polygon then to fit inside the circles. And this basically just tells me how much area, if I fly at 1,000 meters, it will actually be covered. So now we want to know what the flight line is, so I need to measure in halfway, so 300 meters instead of 600. And this tells me where the flight line is going to go. Alright, so then I make a path here, and I want to make that path right between, so that, again, all those, so that it's 300 meters from each side of the polygon. I know now that if I fly this flight line at 1,000 meters, that the area that I've drawn will for sure be covered. And after we generate all of the flight lines we want on Google Earth, then we can take those flight lines and take the endpoints of each line and put them in our flight plan. Then all we do is plug the computer into the airplane, into the autopilot using the USB, turn the plane on, and then we upload.
The fifth and final application to be discussed is emergency response. Emergency response applications consist of flood and other disaster management, search and rescue capabilities, and law enforcement. A popular application at the Utah Water Research Lab is flood management.
After a major flood event, it's important to do a field assessment of the damage. It's very difficult to get in and do a ground view of what's happened. You still got water there, you've got debris, you've got banks that are crumbling and failing. There's a lot of risk to personnel to be in there. Plus there's homeowners to deal with and property, and there's a lot of security issues. So it's really important to get a flyover. Typically you fly over in a plane or a helicopter. It's expensive. It's also difficult to arrange the permits. It's difficult to arrange the personnel to do it. But even then, when you fly over, you can't really create a map from the photographs you take because they're not referenced. They need to be what we call geo-referenced. The Aggie Air Force is it's pennies compared to what it would cost to do a commercial flight. Very importantly, it allows us to look at debris. Is there potential risks still there? We can identify where the sediment deposits have been. It allows us to go in and plan how we're going to do the remediation to recover from the flood. So this is just invaluable to a floodplain manager or somebody trying to deal with a flood disaster.
This is our trailer. This is what we operate from with our service center. Of course, not everyone needs this trailer like this. You could use a canopy and a table and some chairs, or you could operate everything through the cab of your truck too if you want. While flying a plane, you need at least two people. One to monitor the ground station, and then you'll need another person to do the launching, to take manual control if needed, and we call that person the pilot. So there's the GCS operator, the ground control station operator, and also the pilot. All the equipment displayed on this table is the minimum amount of equipment that you would need to run the planes. So this here is a backup box. It's got all of the equipment for the plane, some batteries, extra props, some other stuff, another extra motor just in case yours gets wet and malfunctions. You can replace it in the field. And then this is the transmitter. This is what you use to manually control the aircraft. So the backup box and the transmitter are included with every aircraft. And then you'll need a computer for the ground station to monitor what's going on the aircraft, where it is, and then also to command the UAV, tell it which part of the flight plan to execute. And then you'll need little tools just to kind of do maintenance sort of things, also repairs. Not a lot's required. And the most important tool is tape, just to make some adjustments in the field. When you get back to the lab, you can patch it up a little more so it looks better. But in the field, this is all that's required, just some tape to get things going again if you need to. You'll need a GPS receiver to help you mark some of the waypoints. You'll need to have some radio so that you can communicate with your crew members. And then some cables for programming the aircraft and hooking up the modem here, which is used to communicate to the aircraft. And you'll need an antenna for that. And then also, if you want to do some battery charging in the field, you want a nice battery charger. And of course, you'll need the bungee to launch the aircraft and a nice, fairly large stake to stake the bungee into the ground. And then you'll also need this retriever system, which every plane comes with a transmitter, and if the plane goes down for any reason, then you can find it with this and the transmitter on the plane, and you can find it.
Auto 2, I mean...
Yeah, underneath that, does it say okay?
Yeah, absolutely. Okay.
Alright, yeah, that's awesome.
Okay, you're 0, you're there, buddy.
Our experience at the Utah Water Research Laboratory over the past 2 years has proven to us that the current AggieAir platform is mature, stable, and can provide information of enormous value to natural resources managers. Future versions of the platform that are now under research and development will have greater flight distance and new and more powerful payloads that will be appropriate in addressing an even wider range of natural resources issues.
If you want to learn more about AggieAir and how to purchase a platform for your organization, please visit aggieair.usu.edu.